So we continue our morning session, and the next report will be by Professor Naoya Ando from Kumamoto University from Japan. So I with the report surface with zero mean curvature vector in four-dimensional spaces. So I invite Professor Ando, please.
Thank you very much. I'd like to express my thanks to the organizers of the conference, AGMA, for giving me this chance of the talk. I will talk about surfaces with zero mean curvature vector in four-dimensional spaces. Let N be an oriented Riemannian for manifold. Then we have a bundle decomposition of the twofold exterior power of the tangent bundle of N into two subbundles. This bundle is of rank 6, and these subbundles are of rank 3. We have this decomposition by Hodge's star operator. The twistor spaces associated with N are the sphere bundles in these subbundles, defined by this. H hat here, H hat is the metric induced on the twofold exterior power by the metric of N. Let M be a Riemann surface and F a conformal and minimal immersion of M into N. Then F gives the lifts, the twistor lifts theta F plus minus of F. These are sections of the twistor spaces associated with the pullback bundle by F, defined by this. Where Xc1, Xc2, Xc3, Xc4 form a local orthonormal frame field of the pullback bundle. We suppose that Xc1, Xc2 are tangent to the surface. Let sigma be the second fundamental form of F. We consider sigma to be a bilinear form on the complexification of the tangent plane of the surface and valued in the complexification of the normal plane. Let W be a local complex coordinate of M, and we define sigma WW by this. Then Q, defined like this, does not depend on the choice of a local complex coordinate W, and we can define a complex quartic differential Q on M. If N is a four-dimensional Riemannian space form, then it follows from the equations of Kodachi that Q is holomorphic. Then we have this fact. The following 6 conditions are mutually equivalent. Condition A, at each point of M, principal curvatures do not depend on the choice of a unit normal vector of F. Condition B consists of two relations between the metric and the second fundamental form. Condition C states the complex quartic differential vanishes. Condition D, one of the twistor lifts theta F plus minus is horizontal with respect to the connection nabla hat of the twofold exterior power induced by the Levi-Civita connection nabla of H. Horizontality means that the covariant derivative of theta F plus minus, one of theta F plus minus vanishes. condition E, one of the complex structures IF plus minus is parallel with respect to nabla. each each twister lift corresponds to a complex structure of the pullback bundle. Condition F, we have one of these relations. These relations are concerned with the second fundamental form sigma and the complex structures. We said that a minimal immersion F is isotropic if F satisfies one of the above 6 conditions. We see that A, B, C, and F are mutually equivalent. We immediately see. And also we immediately see that condition D and condition E are equivalent. In addition, condition A and condition D, condition, just a moment. Condition A and condition D are equivalent. This was obtained by Friedrich. Suppose that N is the Euclidean force space, then the twistor spaces associated with E4 are given by the product bundle. And an isotropic minimal surface is given by the composition of an isometry of E4 and a holomorphic immersion into C2. Suppose that N is the fourth sphere, then the twistor spaces are given by this homogeneous space SO5 over U2, which is considered to be CP3, the complex three-dimensional projective space. And an isotropic minimal surface is given by the composition of the twistor map, Penrose twistor fibration, and a holomorphic and horizontal immersion into CP3. In the following, let N be an oriented neutral form manifold. This means that the metric is indefinite and has a signature plus, plus, minus, minus. Then the metric H induces an indefinite metric H hat of the twofold exterior power of the tangent bundle with signature 2, 4 plus, 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 minus, 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 minus. We have a bundle decomposition. This bundle is of rank 6, and these two sub-bundles are of rank 3. Then we see that these sub-bundles are orthogonal with respect to H hat, and the restriction of H hat on each of these sub-bundles has a signature 1, 2. The space-like twistor spaces associated with N are fiber bundles in these sub-bundles given by this. The space-like twistor spaces are analogs of the twistor spaces associated with oriented Riemannian form manifold. Each fiber of the space-like twistor spaces is a hyperboloid of 2 sheets. Let M be a Riemann surface and F a space-like and conformal immersion of M into N with zero mean curvature vector. Then F gives its space-like twistor lifts. These are sections of the space-like twistor twistor space is associated with the pullback band defined by this. And notice that this is a minus plus. We suppose that Xi1, Xi2 are space-like, and Xi3 and Xi4 are time-like. And since we suppose that the surface is space-like, so we suppose that Xi1, Xi2 are tangent to the surface. Then we have this fact. The difference between factor 1 and factor 2. The difference between factor 1 and factor 2 appears only in condition A. Since the space is neutral and the surface is space-like, non-zero normal vectors are time-like, so we need this condition. We said that F is isotropic if F satisfies one of the above 6 conditions. The time-like twistor spaces associated with N are fiber bundles in these two subbundles given by these. These are also analogs of the twistor spaces associated with oriented Riemannian form manifold. Each fiber of the time-like twistor spaces is a hyperboloid of one sheet. Let M be a Lorentz surface. This is an analog of Riemann surface. A Lorentz surface is a two-dimensional manifold with a holomorphic system of paracomplex coordinate neighborhoods. Let F be a time-like and conformal immersion of M into N with zero mean curvature vector. Then F gives its lift of its lift. These are sections of the time-like twistor spaces associated with the pullback band defined by this. We suppose that Xi1, Xi2 are space-like. Since the surface is time-like, we suppose that Xi1, Xi3 are tangent to the surface. Then we have these two facts. Fact 3.1. The following are equivalent. Condition B and condition C correspond to condition B and condition C in factor 2 respectively. Here, this double is a local paracomplex coordinate of a Lorentz surface M. So Q is a paracomplex quartic differential defined on a Lorentz surface M. We said that F is isotropic if F satisfies one of the two conditions. Factor 3.2, the following are mutually equivalent. Condition D, one of the time-like twistor lifts is horizontal with respect to nabla hat. Condition E, one of the paracomplex structures corresponding to the lifts is parallel with respect to nabla. We have condition F, we have one of these relations. In addition, if F satisfies one of the three conditions, then F is isotropic. We said that F is strictly isotropic if F satisfies one of the above three conditions for the orientation of N. This means that the orientation of n naturally chooses one of the time-like twister lifts. It is possible that although f is isotropic, the covariant derivatives of the time-like twister lifts are not zero, but right-like. So there is a gap between the isotropicity and the strict isotropicity, although we choose the orientation of n. We have this proposition. Both the covariant derivatives of the two time-like twister lifts are right-like or zero if and only if f satisfies one of the following. Condition A, the shape operator of a right-like normal vector field vanishes, and then Q vanishes. Then F is isotropic. Condition B, the shape operator of any normal vector field is zero or right-like, and then Q is null or zero. Then F is not isotropic. Isotropic in general. But by this proposition, it is natural to have interest in not only condition A, but also condition B. Suppose that n is a four-dimensional neutral space form. Then n is, then n is, n is E42, S42, or H42. We can suppose that n is E42, S42, or H42. Condition A implies that a right-like normal vector field of the surface is contained in a constant direction. A constant direction is considered to be E42 or E52 or E53. The conformal Gauss map of a time-like surface in a three-dimensional Lorentzian space form of Willmore type with zero holomorphic quartic differential satisfies condition A. By the equations of Gauss-Kudach-Rich, we obtain the following theorem with respect to condition B. Let F be a time-like and conformal immersion of M into N with zero mean curvature vector. Then if satisfies condition B, if and only if these three conditions hold, if satisfies these three conditions, the curvature K of the induced metric by F is identically equal to the constant sectional curvature L0 of N. And the second fundamental form sigma of F satisfies a right-like condition. This is slightly complicated. The curvature tensor of the normal connection nabla hat of F vanishes. The Gauss-Weingarten equations for surfaces satisfying condition B are given by these equations. These matrices A, B are given in the form. This condition corresponds to the curvature condition. This equation corresponds to a right-like condition. Right-like condition. And gamma appears in these and this form mean that the normal connection, the curvature tensor of the normal connection vanishes. this talk has just finished. Thank you very much for your attention.